In the wee hours of August 27th, 1962, an Atlas Agena two-stage rocket was launched from Cape Canaveral in Florida. It carried Mariner 2, the first successful robotic spacecraft to travel to another planet, the planet Venus, which it flew past on December 14th. Later in the semester, we'll talk more about Mariner 2. We'll talk about the long, curved 300 million kilometer path that it followed to reach Venus. And we'll talk about the amazing discoveries it made there. But for now, we want to take a look at the very beginning of its mission. Because Mariner 2 didn't just go a few hundred kilometers from the Earth, or even a few 100,000 kilometers from the Earth. It went tens of millions of kilometers from the Earth. It escaped the Earth's gravity entirely. How is that possible? What does that mean? That is the agenda for today's lecture. We're going to start out by talking about some ideas of energy and ballistics. Ballistics is the study of motion under the influence of only gravity. So we're ignoring other forces like rocket thrust and aerodynamic drag. And in ballistics, the kinds of energies we're most interested in are the specific energies, the energies per unit mass. There's kinetic energy and potential energy. The kinetic specific energy is 1/2 v squared. The potential energy is g times y, where y is the height above the ground. And the key idea is that the total specific energy remains constant during ballistic flight. So let's imagine we have an object launched up from the ground vertically into the air. How high does it go? Well, we can answer that question using energy methods. First, we calculate the potential and kinetic energies at launch. The potential energy is 0, the kinetic energy is just 1/2 the initial speed squared. At the top, of course, the object is at rest, and so its kinetic energy is 0. So the potential energy up there is g times y max, the maximum y value. That is also the total energy. So the energy at the top has to be the energy at launch, and from this we can figure out what the maximum altitude for the object is. We are, of course, making some assumptions. And the first assumption is that the motion is ballistic, that the only force is gravity. And that's okay. We recognize that as a simplification, but it's a good assumption. The second assumption is that the acceleration of gravity, little g, is constant. It's whatever the value is at the surface of the Earth. Now, as I said, assumption number 1 is okay. We know it's a simplification. But assumption number 2 does not hold if the projectile is launched a long way up. And we're assuming that the maximum altitude it achieves is some value that's very much less than the radius of the Earth. But what if it's not? To understand what's going on, we need to look at the big picture. So here's the picture we've been drawing. We're near the surface of the Earth. The surface of the Earth appears flat. The gravitational acceleration at every point above the Earth appears constant. It's the same in direction. It's the same in magnitude. But this picture is only a tiny part of the big picture. The Earth is curved. It's a sphere, pretty much. And we're not necessarily near the surface. And if I were to draw the arrows for the gravitational acceleration for this picture, then they would be all around the Earth, pointing toward the center of the Earth. They wouldn't be constant in direction. And the farther away from the center of the Earth you are, the smaller the arrow would be. In other words, the direction of gravity is always toward the center of the planet, and the magnitude of g decreases with distance from the center of the planet. So how does that work out in mathematical terms? Well, it follows Newton's law of gravitation, which says that the gravitational acceleration is g times m being the planet's mass, over r squared, where r squared is your distance from the center. So we have Newton's constant and the planet's mass, and those jointly determine how strong gravity is. So if we look at the mass of the Earth, and this little O plus symbol means the Earth, then we have a total mass of 5.97 times 10 to the 24th kilograms. And so that means we can calculate the gravitational acceleration at the surface of the Earth. At the surface of the Earth, your radius, your distance from the center of the Earth, is 6,370 kilometers, or a little over 6 million meters. And so we can just calculate it, and we get 9.81 meters per second squared. By the way, this combination of g times the mass of the Earth has a value of about 4 times 10 to the 14th meters cubed per second squared. That's a useful number to remember sometimes. So if the acceleration of gravity is not constant, if we have a new law for gravity, we're also going to need a new law, a new formula for gravitational potential energy, the specific potential energy phi. And so let's see where we started. We have, under the assumption that g is constant, we have at a point y above the ground, we have phi equal to g times y. Now, in doing this, we've made a choice. We've chosen to set the zero of potential energy to be at ground level. And this is very convenient, and we use this very happily, but it is arbitrary. And this means that the gravitational potential energy could be negative. If we dug a hole in the ground and went to the bottom of the hole, then our y-coordinate would be negative. So maybe potential energy can be negative. Now let's look at the situation where we have a planet and we're some distance r away from it. Then g is different at different places. G is the g times the mass of the planet over your distance from the center squared. And so we're going to need a new formula, a new equation for the gravitational potential energy. And here it is. This is the right formula. It's that phi, the specific potential energy, is negative g times m divided by r. Note that this is divided by r, not by r squared. So we can get some idea of how this new formula is related to the old formula by considering a graph of the potential energy versus height above the ground. And so that's just a linear graph. That phi is just g times y. It's a line with slope g. But if we switch to the new picture, then phi is minus gm over r. This is a little complicated. We now keep track of the distance from the center of the planet, and this vertical gray line is, for example, the radius of the Earth, the radius of the ground, and so we're really most concerned to the right of that at greater distances than the ground. And here phi is minus gm over r. It's this negative function. It's always negative, and it approaches 0 at large r. Here's the key: that the picture, the old picture on the left, is a little tiny piece of the picture on the right, a little tiny piece near the surface of the Earth, and in that little tiny piece, that function, that curve, looks like a straight line. Okay, two more things to think about. One is that phi is always negative at any distance. And the second is that phi becomes 0 when you're very, very far away, as r goes to infinity. Okay, this does seem a little strange. I mean, after all, kinetic energy can never be negative. It's 1/2 v squared. We're talking about specific energies, energy per unit mass, and v squared is always positive. And it makes sense because there's a definite zero of kinetic energy. The specific kinetic energy is 0 when you're at rest, because kinetic energy is energy due to motion. But the same is not true of potential energy. Where we choose to make potential energy equal to zero is an arbitrary choice. And before we chose the ground level. That was convenient when we were moving close to the ground. But now it turns out to be most convenient, and we get the simplest formulas, if we choose the zero of potential energy to be very, very, very far away, infinitely far away from the Earth. And that means that every place closer to the Earth than that is below that point, and so the potential energy is always negative. And because the potential energy can be negative, the total energy can be negative too. Let's see how to work a ballistics problem with our new potential energy formula. As before, the total specific energy is just the sum of kinetic and potential parts, and it might be positive or negative, and the total energy remains constant during ballistic flight. Now, let's suppose we have something launched from the surface of a planet. It goes up to some height, and then it turns around and falls down. So how far does it go? How do we figure that out? Well, the first thing we do is we find the total energy by adding up the kinetic and potential parts at the launch. Neither of these is zero. The kinetic part is positive, the potential part is negative, and depends on what the radius of the planet is. And then we set this energy equal to the total energy at the top. Now at the top, the projectile has come to rest, so its kinetic energy is zero. And so the total energy is just minus gm over the maximum radius, the maximum radial distance from the center of the planet. And that means that the maximum radius is just minus gm over the energy. That's not negative because the energy itself is negative. Let's use this new formula for gravitational potential energy in order to solve a problem. The problem is the problem of a sounding rocket. We have a certain rocket. We're going to launch it straight up from the surface of the Earth, and its initial speed is 5,000 meters per second. By the way, that's about equal to the delta V of the Jupiter missile that we analyzed in our class discussion. And that picture on the right there is a picture of the first launch of the Jupiter missile. So how high does this rocket go? It's moving pretty fast, so it's going to go really far up, and so our previous picture is just not going to be good enough. So let's write down the things we know. We know that its initial speed is 5,000 meters per second. And we know that its initial distance from the center of the Earth is the radius of the Earth, about 6.37 million meters. And we also know that the product, g times the mass of the Earth, is about 4 times 10 to the 14th meters cubed per second squared. All right, so from that we can calculate the initial specific kinetic energy, which is 1.25 times 10 to the 7th joules per kilogram, and we can write down the initial gravitational potential energy, which is not zero, but is instead minus 6.25 times 10 to the 7th joules per kilogram. And the sum of those two is the total energy. And that's about minus 5 times 10 to the 7th joules per kilogram. That's negative, but it's okay that it's negative. So all right, that's where we start. That's the total energy. Now let's consider the top of the trajectory where the sounding rocket is momentarily at rest. There, that gravitational potential energy at R max is the total energy. And so from that we can work out that R max is 7.96 times 10 to the 6 meters. It's positive because both there's a minus sign and E is also negative. And that's about 7,960 kilometers, almost 8,000 kilometers from the center of the Earth. Well, how high is that above the surface of the Earth? Well, the altitude is just that number minus the radius of the Earth, which is 1,590 kilometers. The sounding rocket goes to a height 1,590 kilometers above the surface of the Earth. What if we tried to work the same problem using our old formula for gravitational potential energy? We found in our calculation just now that, that the rocket reaches almost 1,600 kilometers above the surface of the Earth, 1,590 kilometers above the surface of the Earth. But suppose we'd just naively applied our old expression for the total energy of the projectile. That the gravitational potential energy was just g times the height above ground. If you do that, then the maximum altitude is just the initial speed squared over 2 times g. And if you substitute 5,000 meters per second for this, you get 1,276 kilometers. That's a lot lower than that. It's more than 300 kilometers lower than the rocket actually goes. Well, why is this? This expression assumes that the strength of gravity is the same everywhere on the sounding rocket's trajectory. But in fact, the rocket goes so high that the force of gravity on the rocket is substantially less near the top of its trajectory, and that allows it to go quite a bit higher. This raises an interesting possibility. So let's consider the sounding rocket problem again. The total energy, which we calculated at the surface of the Earth, was negative. It was because the negative potential energy dominated the positive kinetic energy. And therefore, at the maximum radius from the Earth, the energy was all potential energy that was also negative, and that's okay. That worked out fine. But if we were to increase the launch speed, that is to say, make the initial kinetic energy larger, then we could increase the speed enough so that the total energy was greater than or equal to 0. And if the total energy is greater than or equal to 0, that's equal to the potential energy at no radius, because the potential energy is always negative. In other words, if the energy is greater than or equal to 0, then there's no maximum distance possible. In other words, the object escapes the Earth. It continues moving upward forever. It is not true that what goes up must come down. If it goes up fast enough, it will never come down. Okay, so this tells us how to figure out the escape speed. The escape speed is the initial speed that would make the total energy equal to 0. In other words, 1/2 escape speed squared minus gm over r should be equal to 0. And so that tells us what the escape speed is in terms of r. And here's the formula. The escape speed is the square root of 2gm over r, where m is the mass of the planet and r is your initial distance away from the planet. Now, let's work out an example with this. Let's suppose we're escaping from the Earth's surface. Let's put in the values for the Earth's mass and the Earth's radius here, and we can do this calculation, and we find that the escape speed from the Earth's surface is about 11,200 meters per second, or about 11.2 kilometers per second. And if we launch a rocket into space, that rocket must achieve this speed in order to escape the Earth. You might recognize the equation, or at least recognize that the equation for escape speed is a cousin to an equation that we've already seen in our class. And that equation is the equation for the speed that you have to be traveling to be in a circular orbit around a planet M with an orbital radius r. And that's the circular orbit speed is the square root of gm over r. The escape speed is exactly the same, except there's a 2 inside. It's the square root of 2gm over r. Which means that at a given distance from a planet, the escape speed is always equal to the square root of 2 times the circular orbit speed. Near the surface of the Earth, the circular orbit speed is about 7.9 kilometers per second. The escape speed is about 11.2 kilometers per second, which is the square root of 2 times 7.9. It's about 40% larger than the circular orbit speed. The square root of 2 is about 1.4. So this is a good rule of thumb, that the escape speed is not quite half again as much as the circular orbit speed. What if I'm moving actually faster than the escape speed? Suppose I launch a rocket into space with a speed greater than the escape speed. What happens? Well, what that means is that when we escape the planet, when we get very, very far away, we still have some energy left over as kinetic energy. We still have kinetic energy left over. Let's work it out. Your total energy is, at launch, is 1/2 times your speed squared minus gm over r. That's kinetic plus potential. When you're very, very far away, the gravitational potential energy is 0. And so that's just equal to your kinetic energy very far away. That v infinity is the speed that you're traveling when you're extremely far away, when your distance from the planet is effectively infinity and your potential energy is effectively 0. Okay, so your total energy is 1/2 your distant speed, your infinity speed, your infinitely distant speed is squared. All right, so let's take an example. Let's suppose we launch a rocket from the surface of the Earth, and we make that initial speed 11,700 meters per second instead of 11,200 meters per second. That is to say, we're just 500 meters per second above the escape speed. What is this residual speed, this sometimes called an asymptotic speed, v infinity? What is the speed at a very great distance? And the answer is a little bit surprising. So we go ahead and we calculate the speed at launch, and the speed we calculate the energy at launch, and the energy is positive, as we expect, because we're traveling faster than the escape speed. And then when we solve for the from v infinity, we find that v infinity is 2,370 meters per second. So if we have 500 extra meters per second when we launch, we end up not just with 500 extra meters per second at the end, but with more than 2,000 meters per second residual speed, leftover speed, after gravity has done its worst and I have completely escaped the Earth. By the way, it's worth noting here that what we're calculating are scalars. There's no sense of direction here. That the escape speed is a speed that's sufficient to escape no matter which direction you launch. You don't have to go straight up. As long as your future trajectory doesn't actually hit something, you will escape to infinity, no matter which way you travel. Escape speed, physicists would say, it's a scalar. It doesn't have direction. Let's apply these ideas of kinetic and potential energy to another important situation, the situation of a circular orbit. Let's suppose we have a satellite that's orbiting a planet of mass m in a circular orbit of radius r. So let's use what we know to find a formula for its total specific energy, E. All right, we need to recall that the radius of the circular orbit is related to the speed of the circular orbit. That is to say, the circular orbit speed is the square root of gm over r. So that means that the total energy is the sum of kinetic energy and potential energy. It's 1/2 the square of v circ minus gm over r. But that's just 1/2 gm over r minus gm over r. And that just gives me minus gm over 2r. It's just minus 1/2 gm over r. The kinetic energy and the potential energy are related to each other. In fact, for a circular orbit, the kinetic energy is equal to just minus 1/2 the potential energy. The potential energy is negative, the kinetic energy is positive, and 1/2 the magnitude. Okay, so that's a really nice equation. It means that the energy of a circular orbit, total energy, is always negative, and the bigger the orbit, the closer that is to 0. So it means you have a higher energy for a bigger orbit. A higher orbit with a larger radius is an orbit with a slower orbital speed, so its kinetic energy is less, but it has a higher total energy because its potential energy is much greater. Which brings us to one of the most remarkable surprises of this whole business. So, let's suppose we are a satellite orbiting a planet. Let's say this planet. This happens to be a radar globe, a map that's on a globe of the planet Venus, which I've chosen in honor of Mariner 2. So let's suppose we're orbiting our planet in a nice circular orbit, and as we orbit around the planet, let's suppose that another force does act. Aerodynamic drag in the outer atmosphere of the planet produces a drag force on our satellite. what happens to the motion of the satellite due to aerodynamic drag? Well, if the drag's not too much, what will happen is that it will stay in a circular orbit, but that circular orbit will change. So the effect of drag is to reduce the energy of the satellite. If there was no gravity involved, then that would cause the satellite to slow down. But gravity is also involved. Reducing the energy of the circular orbit causes the orbit to get smaller, to get lower, to have a lower value of r, because a closer orbit has a lower energy. So the net effect of drag is to cause the orbit to get smaller, to the radius to get smaller. But notice what that means. The smaller radius circular orbits have higher orbital speeds. So paradoxically, the net effect of a little bit of atmospheric drag on a satellite in orbit around a planet is to cause the satellite to get lower and faster. The satellite speeds up. So put it this way, suppose we were standing in one place on this planet looking up, and every so often, every 90 minutes let's say, a satellite goes over our heads as it orbits around. And now suppose there's a slight effect of aerodynamic friction, drag on it. What will happen? The first thing I'll notice is that the satellite shows up a little early. It comes by in 87.5 minutes or something, and also it's lower. But the first thing I'll notice is that it's early. It's a tremendously strange paradoxical effect of gravity, that the effect of friction, in this case for an orbiting body, is to actually cause the body to speed up. It's one of the fascinating paradoxical conundrums of satellite motion, which we'll dig into a lot more later on. But for now, I just want you to know that the effect of aerodynamic drag is actually to speed things up. Okay, that's our story for this time. We find that if you're going to go way out into space to explore other planets, you have to escape the Earth. And in order to do that, you have to go fast enough. You have to achieve escape speed. Now, to find out what the escape speed is and to analyze these problems of going very far away from a planet, we're forced to rethink our notion of gravitational potential energy. And that lets us solve all kinds of interesting problems and actually presents us with the true paradox that friction can actually speed you up. So that's it for this time. We'll catch you in the next lecture when we'll be talking about something completely different. But keep this in mind as we discuss the exploration of space using rockets.